sklearngaussianprocesskernelsSum. Description: the SUM kernel in scikit-learn's Gaussian process framework is a powerful tool for combining multiple kernels into a single, more complex kernel. This allows you to model a wider range of relationships within your data. Essentially, the SUM kernel calculates the sum of the output of each individual kernel it encompasses. This can be useful for capturing different aspects of your data, such as both short-range and long-range correlations. Inputs. Input 1 kernel 1. This is a scikit-learn kernel object, such as the RBF kernel, the linear kernel, or even another composite kernel. The first kernel in the SUM. Input 2 kernel 2 optional. This is another scikit-learn kernel object. You can add as many kernels as you need for your model. The second kernel in the SUM. Outputs. Output 1 the SUM kernel. This is a combined kernel object that represents the sum of the individual kernels. The resultant combined kernel. Output 2 covariance matrix. The SUM kernel, when applied to data, generates a covariance matrix that reflects the combined effects of the individual kernels. The matrix representing the covariances between points, as calculated by the combined kernel. Steps. Step 1. Initialize the SUM kernel. Create an instance of the SUM kernel by passing the individual kernels as arguments. Step 2. Apply the kernel. Utilize the combined SUM kernel within your Gaussian process regression GPR model, using the kernel parameter metrics. Metric 1 mean squared error MSE. This commonly used metric assesses the average squared difference between the model's predictions and the actual values. Metric 2 root mean squared error RMSE. The square root of the MSE, providing a more easily interpretable measure of prediction error. Visualization plots. Visualization plot 1 scatter plot of data with the fitted Gaussian process model. This plot helps visualize the model's ability to capture the underlying relationships in your data. Visualization plot 2 heat map of the covariance matrix. This plot helps visualize the relationships between data points as defined by the combined kernel. Fine-tune parameters. Parameter 1 parameters of individual kernels. Each kernel within the SUM kernel will have its own set of parameters. Fine-tuning these parameters, e.g., length scale for the RBF kernel, is crucial for achieving optimal performance. Parameter 2 hyperparameters of the Gaussian process model. The model itself has parameters that need to be tuned, such as the noise level, to find the best fit for your data. Uncertainty methods. Uncertainty method 1 predictive variance. The SUM kernel can be used to estimate the uncertainty of the model's predictions. This is represented by the variance of the predictive distribution. Uncertainty method 2 confidence intervals based on the predictive variance. You can calculate confidence intervals around the model's predictions, providing a visual indication of the uncertainty. Challenges and fixes. Challenge 1 overfitting the SUM kernel. When used with too many kernels or inappropriate parameter settings, can overfit the training data, resulting in poor generalization to new data. Sample use case that resulted in challenge 1 adding multiple kernels to model a complex dataset without careful consideration of the underlying data structure can lead to overfitting. Fixes to challenge 1. Reduce the number of kernels. Start with a smaller number of kernels and gradually increase complexity as needed. Use regularization techniques. Techniques like L1 L2 regularization can help penalize complex models and prevent overfitting. Perform cross-validation. Use cross-validation to evaluate the model's performance on unseen data and identify overfitting. Challenge 2 computational complexity with many kernels. Calculating the covariance matrix can become computationally expensive. especially for large datasets. Sample use case that resulted in Challenge 2 modeling a dataset with millions of data points. Using a SUM kernel with multiple complex kernels. Fixes to Challenge 2. Optimize the kernel parameters, carefully choose and tune the parameters of the individual kernels. To minimize computational complexity, use sparse approximations techniques like sparse Gaussian processes or inducing point methods. Can reduce the computational burden by working with a subset of the data. Consider alternative models, explore other machine learning models that may be more computationally efficient, depending on your data and requirements.